Let's talk about some of the simplest ordered set implementations that we could achieve. So for our simple implementations, we'll assume that we'll be using lists versus arrays. And for lists, we'll make the assumption that they're doubly linked. That adds a little bit more space to each node, but as we've already seen, it gives us the ability to go to the previous node, which seems beneficial here. Let's also talk a little bit about how we'll be storing data. So we could leave the data completely unordered or ordered. You'll notice that these are almost identical to the sorts of issues we encountered when we were talking about priority queues. Okay, so let's go ahead and look at our operations: insert, remove, contains, min, and max, and then each of our different 4 combinations of implementations. So we'll start off with the unordered linked list. So in order to insert something into the unordered linked list, remember, keys are distinct, so we can't just simply tack onto the end or the front of the list. Instead, we have to iterate through the entire list and make sure the key isn't already there. Of course, removing something, we'll have to determine whether it's in the list first, so we'll have to iterate through it. Contains, we can make the same argument for. Since it's unordered, to find the minimum item, we'll have to traverse through every item in the list. So it's also order n. Finding the maximum item is the exact same argument. Okay, so what about an ordered linked list? If we keep things in order, what gets better? Well, in order to insert something, we'll still have to iterate through the items in the list until we find the insertion point. We have to check the list to make sure that we're not inserting a duplicate. So insert is going to be the same. Remove is also going to require us to traverse through the entire list until we find something. If we're lucky and we find it early, we may be able to stop early. But in the worst case, we'll have to go through all the items. Ditto for contains. On the bright side, min and max get quite a bit better. If we've got a doubly linked list with both head and tail pointers, we can of course easily get to the first item in the list. So if they're ordered, we'll be able to easily get to the minimum. And again, we could also easily get to the maximum item from the tail node. Okay, let's talk about the unordered array. So we've got an array. The insert may have to grow the array. So that's order n typically anyway. And the process of keeping, and we'd have to iterate through, and the process of keeping things distinct would require us to go through all n items. Remove will require us finding the item first. If they're in no particular order, we may have to look through all the items. And then to remove something, we may have to move items over in order to keep all of the data contiguous. So that's also order n. Contains, of course, we'll have to look through all possible items until we find something. In the worst case, we might have to look through everything. Minimum, we'll have to look through everything to find the minimum item. Ditto for maximum. What about an ordered array? So very similar to the ordered linked list are 2 operations that depend on ordering. Min and max get quite a bit better and become constant time. One other operation also gets better. Take a minute to see if you can figure out which one it is. If you guessed contains, you're right. So if you remember contains, contains can use binary search to find items and log n time. So let's talk about implementations for iteration. So here we're worried about iteration that moves to the previous or the next item in order based on key. So if we're entirely focused on moving to the next item, the successor, we would go through the data in ascending order, increasing order. If we're only interested in moving to the previous item or the predecessor, we would go through the data in descending order or reverse order. Okay, so the operations we'll focus on here are the previous to the next operation. So previous going to the value with the next lowest, the key with the next lowest value, and next would go to the key with the next highest value. So for our unordered linked list, our first implementation, just to find the very first item, either for previous, we'd start off at the maximum item and we'd have to go through all of our unordered data in order to find it. Or next, we'd have to find our minimum item to start with. And then once we found that minimum, we have to find the second minimum. So we'd have to iterate all of the data, finding something that's larger than the item that we're currently on, but smaller than every other item. Once we're to our third item, our next, we have to find the next largest item. So we have to iterate until we find something that is larger than the item we're on, but smaller than any of the other items that are larger than what we're on. Okay, so the process is a little bit complicated, and in both cases, they're order n in the unordered linked list. For the ordered linked list, however, things are in order. We just go forward or backwards. So forward with the next operation, backwards with previous. Unordered array, again, we have to put in a lot of effort to find the item that is the next largest or the next smallest. But the ordered array, again, we're back to constant time operations. Okay, so after looking at all these operations, we've noticed that a lot of them are order n. And our goal, it'd be nice if all operations were sublinear. So that is, if they're all less than order n. Now, we can't necessarily guarantee constant time for all operations, but hopefully we can do better than order n. And just more specifically, with the hash table, we could get order 1 occasionally, but we would like to get sublinear times all of the time without the additional assumptions. So the hash table had these additional assumptions, like that the hash function was good. That it kind of fairly distributes the data. And it also had this assumption that we were doing rehashing. And remember, rehashing, every once in a while, we'll do some operation that forces us to go through the rehashing process that is order n. Okay, so our goal is to have something that has a little bit stricter guarantees than what we were able to achieve with the hash table.